Hi, everyone. Can you hear me? Hi, GCN. Let me check the return, if it's working. Oh, seems to be working fine. Today, let's talk about the Setun. I don't know if it is the correct pronunciation in Russian, but is the first ternary computer that demonstrated it works. So we can use ternary computing. Unfortunately, it didn't become mainstream because of political things happening during the time, but it's feasible, totally feasible. Nowadays, we have memristors, for example, photonics, spintronics. We can use these things. I'm very interested in the original ISA. So today we are going to cover this. Let me share my screen just a moment. Good. Okay, here we have some original papers that I got surfing the internet. Here we have the original ISA for Setun. It's in Russian. I don't understand Russian, so I need to translate these things. Fortunately, nowadays we have the AIs and also some translation tools that can help us. I have already done that. And if you guys want to have this original paper, it is in my GitHub account. I have an organization called Triquetra, and it's there. So if you guys go to repositories, let me check. I have some examples here that we are going to cover. Here we have some documents that we are translating, but I just recently forked something that's going to be more useful. Just a moment. I don't know why it's not showing up. Later on, I will put the link in the description, but it is a specific repo with a bunch of documents from the original project. So we can check that and translate. I'm going to do this for all these documents. So I'm going to translate all of them. But my first subject is this short document, only 15 pages, and it describes the ISA instruction set and so on, comments, logic, operations, even time. So it's in milliseconds on the right. It's available. I will put the link in the chat, just a moment. But I have already created some applications for us to explore together. Let me see if I can make this bigger. Okay. So there is an application. You guys can play with it, and it's a brief summary of Setun based on the document that I just mentioned. So I have uploaded this document in Gemini and asked it to translate to English, and then to create an article about it, and also a small application that we can interact with. It's this one showing up in the screen. Let me see if I can make it bigger. Yeah, it's bigger. Let me increase the zoom. Okay, here. So here we have some basic information about it, but the interesting thing for me, at least, is the instruction set, the ISA, because with this, we can create a simulator or emulator of Setun. And my plan is to make it emulate Doom, or my objective is to run Doom, the game, that Doom that we know, in Setun. It's not going to be an easy task, but I think it's possible. We can do this with nowadays hardware. It's possible. The main thing here is binary is a subset of ternary. So 0 and 1 is contained in -1, 0, and 1. And that's a good thing. That makes it backward compatible with binary system, and also makes space to additional computing with the -1, that we don't need to make some operations to have a minus sign, or it doesn't matter in ternary computing, because especially in balanced ternary computing, because we already got the minus sign for free. Let me check the comments just a moment. Okay, 3 people watching. Thank you, guys. Here we have the opcode, which stands for operational code. It is in base 9. This is before a conversion that was done later on. The conversion is, for example, actually this is -33, but the conversion here in the Gemini didn't work properly, but we can double check that. If we see the table, there is a minus sign above the number. It's a way of showing that it is a -33 operational code. But later on, based on other papers that I have read, they have created another way of symmetric notation. And that's it. I have created a basic table here and converter, so we can easily convert, for example, actually the number 3 in the nonary mapping table or conversion or symbol conversion, it's X. So what's the deal here? Because if we just put a minus sign above numbers, it's not going to be so easy to read. So those guys at the time, they noticed that and created another way to represent opcodes or numbers in ternary or nonary system. So the W is -4, X is -3, Y -2, Z -1, 0 is 0. So it's really simple. That's where comes the ternary, balanced ternary terminology. The balanced word comes from the around 0. And then we have the positive numbers, normally 1, 2, 3. So the main difference is below 0. So instead of 3, 3, we put x, x. And we can make it happen here. For example, x, x minus, it's going to be like that in base 3, minus 0, minus 0. And in decimal, if we would convert, it's going to be minus 30. And for example, we can mix them together, y and w. Let's see. I have, okay, here, y and w, minus 22 in decimal, and base 3 minus plus minus minus. So later on, I'm going to convert this document and also this small application to make use of these symbols, because they are the state of the art. After a few years after the release of this paper, they have done this kind of symbol conversion. That at the time of the writing of this paper, it was like that. Both of them work. It's just a matter of the terminology and to easily read the operational codes. It's like hexadecimal for binary. It's just a shorter way to read. As you guys may have noticed, for example, here we have 4 symbols, and in symmetric nonary, we only have 2. So if we would do this, for example, mix things together, x, w, okay. So this is a huge number in base 3, and it's half the size in symmetric nonary. So that's the idea. And if we use heptavincimal, which is even shorter notation, it's going to be even less than that. Let me check if I can demonstrate this, because I also have a nonary arithmetic algorithm here that I have prepared. For example, I can use base 3, and let me pick the, okay. Later on, I will put a copy icon here. So we just click on it and the content is going to be copied to the clipboard. For now, I need to select everything. And we go to the nonary arithmetic, choose base 3, use it balance form. Just for remembering, balance form means that we have minus and plus around 0. If it is unbalanced, we have 1, 2, 0, 1, and 2. So that's the difference. So from base 3 balance to nonary, let me check how it's going to be. Original converted. No, that's not what I was planning. Yeah, it's a huge number. Let me check. Ternary. Okay, I was planning to demonstrate the heptavincimal notation to demonstrate that it is even shorter than nonary notation. Okay, here it is. Let's check. Yeah, so it's way shorter than nonary. So that's the goal, to go from one notation to the other, just for the sake of brevity. So we can represent the number with a shorter version. So just for comparison, let's check that stands true. Here it is. So here we have base 3. Let me see if we can increase the size of this thing. I can't. I'm still learning how to use set editor. Base 3 balance base 3. Select that. Balance base 9. Select that. E heptavincimal. Like that. So it's like a heptavincimal. It's similar to hexadecimal, but for base 3. And between the two, we have base 9. And at the time of the Setun, the developers and engineers, they used base 9. So they didn't have heptavincimal. Heptavincimal is a new thing. But at the time, only base 9 was used to represent the number in a shorter way. Let's go back. Later on, I will demonstrate algorithm that those guys also use it to convert from base 2 to 3, 3 to 9, 9 to 10. So it's a way to in software efficiently convert between these bases. So, and we can use mathematical proportions and ratios to go from 3 to 9, for example, very easily. And if we would try to go from 10 to 3 or 3 to 10, it would be a very costly operation. But if we use a bridge from 2 to 3 and 3 to 9 and 9 to 10, it's very efficient. I have demonstrated this in the complexity analysis, space and time with big O notation. Later on, I will demonstrate this. And I even have created some visualization for the conversion steps. And here we have optimized special cases where we can see the big O and the bridge and the notations, special number systems. Here it is. Okay, let's go back to the paper. So the instruction set architecture is here. I have implemented them in a Setun simulator. It's also available in my GitHub account. You guys go to Setun Online Simulator, click on the link, and here it is. So I have implemented almost all of the instructions that we have available. They are here. I will need to convert the code here because I haven't done that yet, but I will do this later on just for clarity. And all the instructions are implemented. Actually, almost all of them. I need to make some code adjustments for the memory manipulation and persistence. But almost everything is implemented. There is also instructions on how to use the emulator. There is a basic program example here. So the first 3 code numbers and positions are for operational codes, and the other ones are used for the actual data that will be acted upon the operational code. And here we have comment input, stop address, and we can even debug. So the step button here we can use to slow down the cycle and see what is happening in each step. We can use the program input here and the data input. They are separated. I have done that because at the time they used string. I forgot the correct name, but a tape. They used a tape, and there was a specific input for the program itself and another specific input for the data. So they didn't have to do everything together. They could separate the concerns. There is also a printer here. And just to make, let's run the program. When we run the program, let's see. So read, I have clicked on read program tape. Then we can go and step. Let's see. That's not what it was supposed to do. Oh, here. I always forget how to properly load the program, because it's trying to simulate the behavior of the computer from the time it was created a couple of decades ago. We need to read the program tape and then load it in the memory. And just after that, we can start the operation or the steps. So right now I will try to do the steps. I will need to fix this because it was supposed to increment the lights here in the adder, but it didn't did that. I will need to check why. Later on, I will fix this. Activate to run, program loaded, start. Yeah, well, I will need to fix this. Aside from the actual instruction set, we have the Ternary Lab. And the Ternary Lab makes possible to represent some numbers. For example, here we can represent the number 9, and we can increment by the base, so base 3, base 4, and so on. And here we have the decimal value. I will add some operations here that made possible to do some operations and multiplications as well. For now, it's only a basic visualization. And we also have the memory and IP2 system. So the memory hierarchy, we have the accumulator, multiplier, index, and control. And we have the car symbols here. Remember that this came from the original paper. And I will need to fix the magnet drum here. And here we have the floating point structure. I haven't delved deeply in this part yet, so I'm still studying this, but it is available as an instruction here, as a mathematical demonstration. But I need to really study this. Right now, I don't know too much to tell about it. I will need to keep reading the translation of the original paper to understand it better. Let me check what else. Okay, yeah, that's it for now. So I will leave the original paper in the video description for you guys to check if necessary. The most important thing here is for me to fix the simulator so it works as expected with each one of these instructions. Even though it's simulated, it should act exactly like a real operation. Let me change the... You can easily change the language here, so it's English or Portuguese. And I have also taken note about this. I will need to fix in a few minutes. Here we have some examples on how to use the simulator and how to read the results. Basically, it's counting some lights that are going to light up here in this panel. Do you guys have any questions? I have previously created abacus to make some demonstrations about ternary computing. Feel free to use it if you want to. It's really fun. It's based on Soroba, which is a Japanese abacus. Okay, if you guys don't have any questions, I will finish this live transmission. Later on, I will create some articles about it and some posts based on this live interaction. Thank you for your participation and see you later.